Hello students, welcome back to the second video on electrostatic potential. In this video, we will discuss about equipotential surface and potential energy of an electric dipole placed in an external electric field. The first topic is equipotential surface. As the name indicates, potential is constant on that surface. A surface on which the potential due to the charge distribution is same at every point is called equipotential surface. Means potential is constant. It is same at every point. These are the equipotential surfaces due to an isolated charge. These blue colored surfaces represent equipotential surface and brown color lines represent the electric field. Let's consider Q charge here. At a distance r, the potential is kq by r. At a distance on this side it is kq by r, here kq by r. If we will consider distance r on all the sides, then potential at all these points are same. That means the surface, this is the surface on which potential value is constant. We can draw another surface here also. The potential is constant. Thus, due to isolated charge, it may be positive or negative, equipotential surfaces are spherical. You can draw so many spheres on which potential remains constant. Thus, due to isolated charge, the equipotential surfaces are spherical. It is shown here, spherical equipotential surface due to isolated charge. Let's see what type of equipotential surface due to an electric dipole. Again here, these blue colored surfaces represent equipotential surface and the brown lines, these are electric field lines. Okay. In this case, the electric field lines are parallel lines, means uniform electric field. These plane surfaces, this plane surface represents the equipotential surface. It is clearly observed here. The equipotential surface is perpendicular to the electric field lines. You can say this case also in case of the dipole or in case of the spherical equipotential surface. In all the cases, the equipotential surface is perpendicular to the electric field. Thus, what are the properties of equipotential surfaces? Number 1, no work is done in moving a test charge from one point to another on an equipotential surface. Since potential is constant, the change in potential del V is equal to 0. Work done W is equal to Q del V. This formula we have already discussed. The work done to move a charge through potential difference del V, W is equal to Q del V. So, del V is 0, W is equal to 0. That is, no work is done to move a charge on an equipotential surface. Second property, the electric field is always perpendicular to the element dl of the equipotential surface. So, electric field makes an angle 90 degree with the equipotential surface. Third property, they do not intersect each other. So, these are the properties of equipotential surfaces. Now, let's see some other examples of equipotential surfaces and what is its significance. Again, here electric field lines are shown, parallel lines. 3 points A, B, C, A, B and C shown in the diagram. This BC surface or BC line, if you will consider BC line, the potential at B is equal to potential at C. This is the part. If you will draw a surface like this, then B and C lies on the surface. So at point B and C the potential is constant, and at point B the potential is less than that of A. Why? Let's compare A and C. The electric potential decreases along the electric field. Electric field line is towards right. So the potential at point C is less than the potential at A, and B and C they have the same potential. B and the C they have the same potential. So potential at point B is lower than the potential at point A, and B and C they are at the same potential. Let's take another example. The surface of a charged conductor. The surface of a charged conductor in electrostatic equilibrium is an equipotential surface. This is the surface, the upper surface of the charged conductor. This is an equipotential surface. And the potential on the surface is equal to also the potential inside the conductor. That is, the potential on the surface is equal to also the potential inside the conductor. So these are some examples of equipotential surface due to different types of charge distributions. The next topic is the potential energy of an electric dipole in an external electric field. If a dipole minus Q plus Q, here it is placed in an external electric field E, then this plus Q experiences force QE, minus Q experiences force minus QE. So net force on the dipole is 0, and the dipole experiences a torque. The torque is equal to tau is equal to PE sin theta. Now the dipole experiences a torque means due to the electric field it experiences a torque. Thus the dipole has some potential energy. What is the potential energy? It is the work done to rotate the dipole from 0 potential energy state to this state. So let's find the work done to rotate the dipole from 0 potential energy state to this theta state. You know what is tau is equal to PE sin theta. Tau is PE sin theta. Let dW is the small work done to rotate it through d theta. Now dW is equal to tau d theta is equal to PE sin theta d theta. Now we have to find what is the total work done to rotate it, for example, from theta 1 to theta 2. Work done to rotate it from theta 1 to theta 2, it is integration of PE sin theta, and PE can take outside. Integration of sin theta is minus cos theta. So putting the limits theta 1 and theta 2, you have W is equal to PE cos theta 1 minus cos theta 2. But what is the potential energy at this position theta? At this position theta, it is the work done to rotate the dipole from 0 potential energy to position theta. 0 potential energy 90 degree, the angle 90 degree with the electric field is considered as the 0 potential energy. So 90 degree, rotating the dipole from 90 degree to theta means putting the values theta 1 here is equal to 90 degree and theta 2 is equal to theta. So here PE cos 90 minus cos theta, that is equal to U is equal to minus PE cos theta. So this is the potential energy of the dipole when the dipole moment makes an angle theta with the field. So potential energy of the dipole is equal to minus P cos theta when it makes an angle theta. For example, it makes an angle 60 degree. Then at the place of cos theta you have to put cos 60. Now the question arises, at what angle the potential energy of the dipole it will be minimum? When cos theta becomes 1, the potential energy will be minus Pe and negative potential energy, and this is the minimum potential energy. Similarly, which orientation of the dipole gives maximum potential energy, or what is the orientation? When theta is equal to 180 degree, then u is equal to minus P cos 180. It is equal to minus P into minus 1. It will give Pe. So let's see what are the conditions for stable and unstable equilibrium. Means at what angle theta the dipole is said to be in stable equilibrium, at what angle it is said to be in unstable equilibrium. So when theta is equal to 0 degree, then putting the value here, minus P cos 0 is equal to 1, so u is equal to minus P. This is the condition of stable equilibrium. Similarly, when theta is equal to 180 degree, then u is equal to minus P cos 180 degree. So it becomes minus P into minus 1 here. It becomes P, and this is the case of unstable equilibrium. And theta is 90 degree, u is equal to 0. Of course, we have considered that point, that position as 0 potential energy. So using this, you can find how much work is done to rotate the dipole from one position to the other position. Here is a question. Find the work done to rotate the dipole from the stable equilibrium state to unstable equilibrium state in the external electric field. Stable equilibrium state means theta is equal to 0 degree, means theta 1 is 0 degree, and finally to unstable equilibrium means theta 2 is equal to 180 degree. Putting these values of theta 1 and theta 2 in this formula, at the place of theta 1 it is equal to 0 degree, at the place of theta 2 it is 180 degree. It is equal to Pe cos 0 minus cos 180 degree. You will get cos 0 is 1, 180 degree cos 180 degree minus 1. So you will get 1 minus of minus 1, it is 2. So you will get the value is equal to, if you will put the value, you will get 2 Pe. So what is the work done to rotate the dipole from from stable equilibrium to unstable equilibrium? It is equal to 2P. Similarly, you can find from 0 potential energy state to stable equilibrium state. Yeah, from 60 degree to 120 degree, you have to, in that case, you have to use this formula. Okay. So this is about the potential energy of the dipole in an external electric field, and the potential energy of the dipole in position theta is equal to minus Pe cos theta, or it can be written as minus P vector dot E vector, because P vector dot E vector is equal to Pe cos theta. Here theta is the angle between P vector dipole moment and the electric field. This is all about the potential energy of the dipole in an external electric field. Okay. So in this video we discussed about equipotential surfaces and the potential energy of the dipole in an external electric field. Thank you.